So this would be the final lecture of the hardware software mini series. Okay, if you remember, we started this whole series with the idea of what I consider as essential hardware knowledge for engineers. Okay, and today's lecture sort of captures the essence of a bunch of things that we've already studied till now. So yeah, let's get started. So standard mindset and principles. We'll focus a lot on reasoning. Remembering facts is not as important as the method of reasoning that we use to arrive at those facts. Thinking is mandatory, blah blah blah, kind of stuff. And you cannot rely on my words. Okay, you've got to continuously apply your own brain to validate whether what I'm saying is correct or not. Okay. All right. So let's review the basics quickly, and then we'll get to the main stuff. The first part, like before the break, we'll focus on a bunch of basics, and the second part we'll get into some advanced stuff. Okay. So given the fact that the AC is not working, we'll try to see if we can still apply our minds post the break or not. But hopefully the break gives us some breathing room. Alright, so you guys will remember this slide from the last lecture, the JVM one. Alright, we would keep the JVM aside for this lecture. We would not be focusing on the JVM. Why? Because JVM is a very, very high level machine. It provides an extremely high level ISA. You guys remember ISA? Yes. Right? Instruction set architecture, right? So for example, we do not get access to memory directly. It's always via, sort of the handle of the object that we end up receiving the access to the memory, right? And there's stuff like, there are instructions like throw, okay, or new. They don't reveal anything about what's going behind the scenes. They are exposing very, very high level concepts to us, right? So in that sense, JVM is it's actually a very object oriented VM. If you remember, we had concluded that you cannot actually, for example, compile a C for JVM. You can emulate C language on JVM because during completeness, but you cannot compile C in terms of it's not going to be natively working on the JVM. Okay, so because of that, we'll keep the JVM aside. Abstraction of the JVM will prevent our understanding of some of the concepts that we want to focus on today. Okay, so we'll get directly into the kind of machine that you use on a day-to-day basis, your laptops, okay, or your servers. So we'll do a quick review of the hardware. We'll focus on the simple pieces. We'll leave out some of the sort of advanced pieces of the hardware. The CPU, we can imagine it as, if you remember there, the execution would happen on a bunch of execution units, and register files, the sort of registers were getting used as scratchpad memory while the instructions are executing. You guys remember that, right? Okay. So, and the instructions and the data would be fetched from memory. There would be a cache somewhere in between on the CPU to accelerate the access to the memory. The instructions would go through a queue and a decoder to convert it into a set of micro instructions. Because ISA is the contract that the CPU exposes outside, but internally it might be using very different mechanisms. So it sort of converts that ISA into its internal micro operations and then executes them. Okay, and you guys would remember the program counter, right? Which at any point in time is pointing to the instruction that is executing or the next instruction, depending upon the architecture, right? You guys would also remember that the ISA can actually be pretty simple. You guys would remember the brainfuck language that we had actually, language or ISA, whichever way you want to think about it. And it was actually a very, very simple language, right? It had only 8 instructions, right? If I remember correctly. So even on the kind of laptops and the CPUs that you would normally encounter, the instruction categories are actually not enough. Basic sort of load store for memory access, loading from memory, storing to memory, control flow, which is branching and if conditions and stuff like that, arithmetic and logical, which is the plus minus multiply divide kind of thing. Okay, CPU thinks in these terms. That's what we want to focus on. What we want to focus on is that given what the ISA gives us are very, very basic primitives, while the kind of language that we use is extremely high level, how do these two get married? This is what this lecture is about. Okay, so because the high level language allows us to program far more effectively, because it allows us to program by thinking about the domain that we are trying to solve for, right? But ultimately that program is going to get compiled and run on the machine, right? If we have an understanding of how the program is running on the machine, in some advanced use cases, it allows us to build magically fast things. Okay, in some other use cases, it allows us to debug things or troubleshoot things in a much more efficient fashion. In some yet another cases, the only way to actually figure out an issue is if you have an understanding of how things actually get done behind the scenes. Okay, so these are the advantages of knowing how some of these programming constructs are implemented. So while we will continue to program in the way that we normally do, we would want to develop an understanding of how these things get implemented behind the scenes. Okay, so given the fact that we want to focus on the bare metal machine, the language that we would be using in this lecture today is C++. You guys don't have to worry about knowing C++. Okay, we'll focus on the conceptual pieces of it. Alright? So, with that, let's do a quick basic check. Let's say that is my memory, my overall memory that is available to me. Okay? What is the total addressable memory that is available to a program? Yes, no? Like in your normal machines, like how much memory is available to the programs? Megabytes, gigabytes, terabytes? No? When you talk about a 32-bit machine or 64-bit machine, what do you normally mean? The moment I said 64 bits, so 2 to the power 64. Walk me through the reasoning. What does it mean to be a 64-bit machine? Do you guys remember our first lecture where we talked about the RAM access? How many address bits were going through? How many lines were connecting the CPU to the RAM? 64 or 72, right? Depending upon whether ECC is enabled or not, right? But 64 is actually the addressing bits, which means that how much total kind of space that you can have? 2 to the power 64, right? Now that's a physical piece of it, and in practice, often enough, CPUs would actually expose out only 48 lines instead of 64. But the idea is essentially that virtually each program has access to 2 to the power 64 bits of memory. 2 to the power 64 bits of memory. Okay. This is the virtual space that is available to programs, which is different from the actual physical RAM. All of you are sort of I don't know whether you are aware about virtual memory management yet or not, but at least intuitively you know that each program, at any point in time, on your laptop, you have multiple programs running, right? Your OS is giving this impression to each program that you have the full memory available to you, right? So one program cannot write into the memory of another program unless explicitly enabled to do so, right? So each program has an address space, has a memory space available to it, okay? And as we discussed, 2 raised to 64, it should be actually bits. Okay? So ranging from address 0 to all bits being 1, okay? is all of this memory addressable by a program? Should all of this memory be addressable by a program? Yeah.
Intuitively, maybe it shouldn't be all accessible. Some portion might be there for like the system itself, or what if the program crashes and then something happens. So in that case, we need some more memory to clear that memory. Like some program.
Good reasoning. So intuitively you feel that some areas might be reserved. Fair point. Anything that is not reserved, does it by default become available to the program?
Maybe initially it will allocate some amount of memory, and later on, if it requires more, it will expand.
Yeah, right. And why would so essentially programs would start with some amount of memory. Then as they need it, the addressable memory becomes more and more, right? Intuitively, why should that be needed?
Maybe because
why not to start off with the full virtual memory space? Yeah.
Maybe because when you have less memory to access from, it'll be maybe easier and faster to access data compared to a lot more. So
remember that memory is addressable in a random access fashion. That's why we call it RAM, which means that it shouldn't matter whether it is less memory or more memory. Whether I access this offset or that offset in the memory, amount of access time is the same. Any other reason?
Would be inefficient use of the remaining space.
Inefficient use of, I think you're on to something. But can we sort of refine that argument a little more?
So it's to have other operations so we can run simultaneously. If all the memory is addressed in the beginning to some operation, we can't use it. We can't perform any other operations or any other program.
Any other program? Yeah, so I think I'll marry these two arguments a little. That if we by default make every bit of memory space available to a program, we've already run out of our physical memory, right? So it might make sense that as and when program actually needs more memory, we allocate it out so that we have some physical RAM available, right? This is the virtual memory part of it. We pick pieces of the physical RAM and make it allocated to the virtual memory area of a program, right? If we by default start with the whole memory space being allocated to a single program, then we can be rest assured that pretty much all of our physical RAM is gone. Make sense? Okay. So, but we should not rely on just this reasoning alone. We should always validate, like engineers should. Okay. So I wrote a small utility. It's called memlength. Okay. For all of this lecture, we'll be using this utility. Okay. It's in the repo that for this lecture code. Okay. So I say memlength dump and a memory address. Okay. Or some memory address I concocted segmentation point, which definitely means that I cannot access any memory. Okay. So there's some truth to what we discussed just now. On the other hand, when I did some other random address, it's not random, but yeah, it's some memory address, I was able to read, okay, the data. Alright, so which means that some parts of the addressable memory I'm able to read, some other parts I'm not able to read. Okay, my operating system kills the process the moment I try to read a non-reachable address. Okay? Alright. Where is the program stored? Outside the memory or inside the memory? Huh?
outside the RAM.
Outside the RAM? Inside the RAM? Outside the RAM?
Outside the RAM.
Okay. Who agrees?
Like the code for the program or the data will be stored outside the RAM, but when it will be executed, it will go inside the RAM.
Yeah, so during the execution I'm talking. Just to be clear, yeah, I get it that obviously the executable file is lying on the disk, but when executing it, you would load it in memory. The question is whether are you loading it in this memory space or are you loading it in some other memory space?
In RAM itself. because it is being run there, so it should be.
It should be in this memory space then? Should be? Who agrees? Who disagrees? Remember, these are like, these are things that we deal with on a day-to-day basis, right? Every day we are running programs. Yet we don't have an understanding of these things yet. It should also be food for thought about why we are not curious enough to figure out how some of these things work. But yeah, again, at least right now we have that opportunity. So should the program that gets loaded be in the virtual memory space of that program or outside of it?
In the virtual memory space.
How many of you believe it should be in the virtual memory space? Let me actually make this a binary question. Okay, so like about 8 to 10 times. Others, I'm assuming, believe that it should be in the virtual memory space.
It should be.
Sorry, what was my first question? It should be. Okay, so 8 to 10 people believe that it should be, and the rest of you believe that it shouldn't be. Right? There's no ternary state allowed here, only binary state. Okay? So anybody who didn't raise their hand, I'm going to assume that that's what you believe. Okay? Sorry?
Code will be stored in cage memory and all the execution will be in virtual memory.
What's called that?
Code files
Yeah.
should be stored in cage memory.
In some caged memory.
Yeah.
Okay.
Cache
Some cache memory. Okay.
and the executions will be in virtual memory.
Execution will be in virtual memory. Okay, that's similar to the point that you were making, isn't it? That while running the process, the machine code should be in virtual memory. Oh, you're thinking it should particularly be in the cached area. Well, what if the program is more than the cache memory? That argument is easily countered with that, right? Okay, so let's say the answer is that there's no easy answer. Okay, but for majority of the machines out there, you would actually have the machine code loaded in the same virtual address space, and this is what is known as a von Neumann architecture. You would see this name get thrown around a lot. I don't expect you to remember it or memorize it. As I said, facts are not important. The reasoning is. Okay? You can always look up a fact. Okay? And it's also a bit of a mislabel because the only reason why it's called the von Neumann architecture is because John von Neumann actually wrote a report on EDAC or EDVAC, I forget the name of the computer that was getting built at that point in time, and he was the first one who actually wrote the report. But he was not the only guy who was actually working on that architecture. A whole team was actually working on it. So in that sense, it's a very, very bad naming that only one person ended up getting the credit. Like as a person, he was obviously very, very accomplished person, but the labeling is a bit of a historical mistake. The architecture of this is load store mechanism, a bunch of instructions, a bunch of control flows, same as the ISA thing that we discussed earlier. Okay? The defining characteristic is that machine code gets loaded in the same address space as where your data is actually getting included. Okay? So that is the defining criteria. Yeah.
So we can also see this like in the example. For example, we put some pen drive and run some executable itself, and then remove the pen drive. The executable still runs.
Yes.
So that.
Yeah, absolutely. Absolutely. That's a good example. Right? That intuitively when once something has been gotten loaded, you can even actually change the file. Forget about ejecting the disk, etc. You can even change the file and it won't change anything about the loaded image, so long as the image has been loaded fully. Okay? Sometimes the instruction, the machine code address space is different from the data address. We refer to this as the Harvard architecture. Assignment for you guys would be, although you guys never complete your assignment, but assignment for you is to think about, is JVM a Harvard architecture instead of a von Neumann architecture? You guys have gone through the JVM's architecture in the previous lecture, so you need to think about whether the memory area where the instructions are stored, is it completely separate from the memory area where the data is stored? Okay? So now we actually start with the actual lecture. All of that was just the bottom of part. Okay? We've got a piece of code. It's in the file memlens.cpp, there in the repo. The question for us is, conceptually, what does the machine code equivalent of this look like? So we've got the source code. What we need to imagine is, how would it actually show up in the machine image? So when you compile any program, there is some machine code that you get, right? So the question for us is, how does it show up in that image? Let's try to apply. I'm going to help you guys, nudge you guys a little, okay? But you have to participate. You have to help me out a little here. I can't be the only one doing the thinking, okay? Fundamentally, there is a bunch of logic in here and a bunch of data points, right? This is a data, like something that is pointing to a data. This is something that is pointing. Variables are data. Variables are data, right? Okay. We have a for loop, while loop. So there's a bunch of logic in here. For loop, if you remember from our previous lecture, can be implemented via conditional jumps, right? So you have some set of instructions here. The instructions would likely be some data is equal to this value, then do a divide, right? Then do a jump back, and if the condition is fulfilled, then continue. If the condition is not fulfilled, then jump out of this area. Yeah. Okay. So logically, we don't need to know assembly. Logically, we can think about how this would be getting implemented behind the scenes. Correct? Yes. Right. Okay. So we know that there's a bunch of assembly instructions that are actually going to get created, machine code that is actually going to get generated, right? So at least part of what that gets compiled is going to show up as machine code in the memory space, okay? Right? The name itself need not actually show, okay? Because remember that the machine code, remember we are not talking about JVM anymore, we are talking about your normal x86 or ARM64 ISA, okay? So your CPU does not work on names, your CPU works on addresses. Remember how CPU thinks? CPU knows only instructions and addresses, that's all, okay? So the name prime factors does not matter. What matters is where exactly prime factor starts. So when I need to call prime factors, I just say call this address, and the CPU will jump to this address and start executing. Okay? Is this part clear? Okay, so there's a bunch of logical instructions, machine instructions that get captured. What happens to these data points? What happens to factors, factor IDX? There's a new something that is getting created. Which one of these data points, their size is knowable at compile time? At the compilation step, what can be determined about these variables? uint32 is a 32-bit, okay? Which means how many bytes? 4 bytes. Okay, size t on a 64-bit machine is a 64-bit, which means how many bytes? 8 bytes. Okay, so during compilation time, I know that factors, wherever it is in the memory, it's going to be a 4-byte wide memory area, right? Similarly, factor IDX is going to be an 8-byte wide memory area. Okay, factors. I also do a new something. So this is an array that is getting created of num32, num 4 byte numbers. Okay, so num times 4 bytes wide area is going to get allocated. Similarly for I will need 4 bytes. So these are some of the facts that I know. Okay. Is num known at compile time? The value of num? Who said no? Yeah. Why?
Because you can take it, anything can happen.
Yeah, you can take it that in as a user input, right? Yeah, that's a good one. Okay? So the value of num cannot be known. Okay? Unless the only place where prime factors gets called, it's getting called with a fixed value. Unless that happens, the compile time value is not known. It's going to be determinable at run. Yeah.
So, but we know how many bytes to store for num.
How many? If the value of num is not known, how do you know?
Because we are explicitly saying it will be a integer 32, like in the arguments, in the function arguments, first line.
Yeah, so you know how many bytes of storage num would need, but you do not know what is the value inside those 4 bytes. Okay, and that value ends up being used to create this array, new array. Correct? So the value of num is not known. The amount of space it's going to take up, the amount of space num is going to take up is known. The amount of space that the array is going to take up is not known because the value of num is not known. Clear? Right? So we have a bunch of variables where the size is known at compile time and a bunch of variables where the size is not known at compile time. Make sense? So largely we can divide it in these 2 buckets. Okay. So how would this logic, clearly this logic is acting on these data points. It's using these data points and manipulating it, right? For example, I at any point in time, I++ means that see that value, add 1 to it and store that value, correct? That is what I++ means, right? So one way to think about this implementation is that right within the code, we have these areas identified, some 4 byte area, some 8 byte area, etc. And we patch these whenever the function gets called. That's one way to think about it. Yes, no? Right? What is the issue with this approach? Remember that when we are seeing the code, the data is embedded right where the logic is. I'm trying to give you this impression of what it would translate into as machine code. If we translate it as is, the answer that we get is we have this set of instructions, and right within those instructions we have these data points embedded, just like we have these variables embedded right between the logic, isn't it? What is the issue if we were to follow this approach? Every time, sorry, somebody was saying something? Wastage of space. That space will still need to anyways allocate. But there is probably some truth to what you said, but probably it will need to be articulated differently. What is the issue that we see? If we were to just blindly, use the same organization of this information, if we were to just blindly copy exactly the same organization onto machine code.
Like while execution, we might not need that space, but that space is
while executing this piece of logic, we will always need this space. Remember, we'll always need factors because the code has been written like this. So long as, unless there is a return, premature return, that space is going to be carved out because you are manipulating factor IDX, IE, all of these things you are manipulating. So space is not going to go to waste. But the issue is that every single time I call prime factors function, the value changes, right? Right? So every single time I'm calling prime factors, should I first patch this memory area and modify the value of num to whatever it is that the argument value that I want to pass at that point in time? So which means every single time I'm calling a function, I'm doing a write also. That's issue number 1. Do you guys see the issue?
yes.
Right? What is the other issue? What if I have multiple threads actually calling the same function with different value of num? What happens then?
if the function doesn't run one after another, then we might face issue where one call is troubling another call.
Yes, right. So one call is part way through, and the other, so there is a race condition in there, right? If we are not thoughtful about it, correct? Okay. Another approach, so given all of these issues, another approach is that we carve out a separate area for the variable, separate from the code, which is very different from how we see the code here. Here we are seeing the code like this. At the machine stage, while running, the automation is looking different. And we say that all of these variables, instead of being here, we allocate them here. And all of this will work so long as the code knows the address of these. Okay, remember that the code accesses variables not by names but by address. Okay, every access that is done, be it for code, like calling a function, or be it accessing a variable, like reading a variable or writing a variable, all of this is always done by address. So long as we know the address of these variables, this code should work. Right? Okay, so this is one way that we can think about, this is another way that we can think about organizing things. Okay, so this was guess.
What about the space of the time, the method?
Sorry, this space? Sorry?
This one, the function space, which we
The function space just has logic. Okay, see, when this function was getting executed, let's say I++, how would it get implemented in machine code? Read the value at address of I, incremented by 1, store the value at the same address. Right? So long as I know the address of I, I'm good. When all of these were embedded right in here, the address would still have been needed. Okay, just that the address was right next door, whereas in this case it's okay. All good? So notice the first difference that happens conceptually between source code versus how it's actually executed on the machine. That the code piece, the logic and the data become disjointed. Okay, so this is where our guesswork ends, and we'll actually quickly validate it. But summary of this is, source code gets translated into machine code. We need to, for some of the variables, we know the size of the variable, and for the code to work, we need to always know the address of each variable. Okay. So let's use Wemlens to understand this. It's the same piece of code, and you guys, I'll encourage you guys to actually compile Wemlens on your own machine and run it on your own machine also. We are using the demo call parameter, and it executes something. It shows the execution logic of this. Okay, there's a main function which calls a print prime factors function, which calls the prime factors function. Okay, so this is the flow of the code that gets executed. But notice this. What is the address of the function? There are three functions that we are calling in here. You guys can look at your screens also. There are three functions: main, print prime factors, and prime factors. For each one of them, their address. Remember that CPU can deal only in addresses. For each one of them, the address is lying where? I have color coded. All of those are yellow, correct? The address of each function is a yellow. That coloring is mine. CPU does not know a color. Okay? Should be obvious, but let me state that. So you would see that 0x something, that's the actual address. And then there is some sort of name that I'm using as an anchor plus some offset. Okay? Which tells us broadly in what area of the memory it is in. I'll explain those areas in a bit. Okay? But notice that each function is in the code area. Are you guys seeing that on the screen? Right? Yes, no, guys, I need confirmation.
Yes, yes.
Okay. What? Sorry?
I was asking code area, I couldn't understand.
I'll explain what the code area is. For the time being, just understand that code plus 26532 means that this function is physically located in the virtual memory space at this address 0x10239667A4, and this address falls in the code area at an offset of 26532. Offset word you understand, right? Meaning the beginning of the code area plus some distance away, and that distance is what I call as offset. Okay, understood? Each function's address lies in the code area. Yes?
Yes.
Okay. What about local variables? A lot of the local variables seem to be on what I am calling a stack. Correct? Yes? And some of the local variables seem to be on the heap. Yeah?
Yes.
Okay? And obviously we get the result of the function also, prime factors over 2, 3, 4, 8. And I also give you a memory dump of the factors variable, which is factors variable is on the heap. Notice this. Okay? Alright, so memory dump looks something like this. 020000, 02000, 03 zeros. Okay? Do you notice something? What are the prime factors? These. What are the values that you are seeing? These. Prime factors were 32-bit numbers, correct? So each one of these is actually, you guys are familiar with looking at hexadecimals or no? More or less?
Less.
Okay. So fair enough. This is not too complicated. 02 means 2 only in decimal also. But the important thing here is this, that 32-bit means 4 bytes. Each pair of characters represents 1 byte. So 4 bytes is 02, 00, 00, 00. This is one number. This is in the Little Indian format, which means that the least significant byte comes first, then the next significant byte, then the next, okay? So this is known as Little Indian, where some architectures run on Big Indian, where the most significant byte comes first, okay? So the way to read this value is starting from here, 00000002, which translates to the number 2. That is the number 2, the first number that you see, okay? So just giving you a feel of that every time you access an array of numbers, how it's actually stored in the memory. Useful to get a sense of how these things work, okay? Alright, so what we noticed is that each function lies in some address space called code, some area called code. Most of the local variables lie in a memory area called stack, and the variable that we initialize using the new keyword is lying in the heap. Factors we use new, right? Factors is lying in the heap. Okay, make sense? All right. So this is what we are observing, and this is what it would look like. The code goes in here, stack goes somewhere over here. By the way, also notice that unlike code plus something, stack is minus. Stack, any name that shows up against stack, there's always, the offset is in minus. Okay, that's because stack grows downwards. So when we say code plus something, the value of code is code anchor. I'm using the name as this. Code plus 100, plus 200, plus 300. Okay? Stack in most architectures goes downwards. This is not your DSA wala stack. This is just memory area that we are calling stack. Okay, just the heap is also not your DSA heap. This is a memory area that I should have called it out before because the nomenclatures are strongly associated in your mind. But hopefully this gives you a sense. Okay, so stack minus, heap plus, code plus. This is how we think about offsets. Okay. How many such areas exist in the memory? Lots. Okay, but notice, so this is .memlens, so memlens layout. You guys can run it on your own machines as well. And it will show you that when memlens was running, what does the operation of the memory look like? Okay, for each, so there are these sort of segments in the memory. Each segment has a start address and an end address. Again, in hexadecimal I am providing the range of that address range. So this is 64 kilobytes. Resident as in physically the memory has been allocated. Remember that some of these pages, even though there's a range, the resident is 0. It means that the range is accessible, but there is no physical RAM backing it. Okay, we use some of these things for a set of reasons that I'm not getting into right now. Permissions. R means I can read addresses in this area, values in this area. Okay, so I can program any instruction that reads from this area. W means I can write to it. X means execute. So this is done for protection reasons. Because if executable is in a writable area, the worry is that a malicious user can write in data and cause a jump to it. And this is actually one of the biggest reasons for memory issues. Okay, so there are ways to bypass this. By the way, just 2 days back, there was a huge vulnerability that got announced. I don't know how many of you heard about it. XZ. XZ is a compression utility. Okay, and it used a particular mechanism, called iFunk. Which is a trampoline mechanism we'll study in the second half of this lecture. To actually execute. So despite the fact that code was marked as not writable and data is marked as not executable, still through some indirect mechanisms we are able to execute stuff. Okay, but those are the reasons why it's useful to understand how these things work. If you don't understand this, then you cannot even understand how that vulnerability actually operates. Okay, so our memlens, we have a code section, a const section. So whenever you have strings, string, right? So a series of characters, whenever you have it, those strings actually get stored in your executable image and get mapped in memory in the const section. So fixed in space, you cannot write it. Okay, and a bunch of other kinds of information. Data is where your global variables. Okay, will go in here. Okay, local variables, remember, will go onto the stack. Okay, and anything that you allocate using new will go onto the heap. Okay, so then a bunch of other sections. You would see a stack section here. Size of the stack section is 7 megabytes, which is not a lot if you think about it. How many of you have ever encountered stack overflow? Okay, almost everybody has, right? Without it, how will we learn not to have infinite recursion, right? We'll get into studying why that leads to stack overflow. Okay, so I'm just giving a sense that the overall memory space is carved out into all of these different areas. Okay, these regions. All right. Anything outside of this region we cannot access, which is why the first time when I accessed a random memory area, the program sec faulted. Okay, the program crashed. So anything outside of these memory addresses we want to access, it will crash. And you can play around with memlens on your own machine. Don't worry, nothing will get corrupted on your machine. Yeah.
So then, how will the data be expanded if we cannot even access the parts outside of it?
Good question. We'll get into that. But if we don't end up covering it completely, let me know and we'll cover it. We can talk about it after the Okay, I'm behind schedule, so we'll take a pause now instead of later. Okay, because the next part is very crucial to understand. What do we know till now? We know that local variables go onto the stack. Okay, so we'll discuss what that looks like right now. What happens when functions end up being called? We'll discuss that. And through this, you will be able to get into an understanding of what happens when your function goes into infinite recursion. Why do you get into stack overflow? Okay. So let's say there was a stack segment in the array. Remember, stack grows downwards. So every time we are adding more and more data, we are demanding more data from the stack. It's going to grow like this. Okay. That's something that all of you are now comfortable with, right? Stack grows downwards. Okay. So we'll use the same call flow that we were seeing earlier. Main function calls a function called print prime factors, which calls a function called prime factors. So we'll see what happens to the stack as we make these calls. Okay. At the beginning, let's say there was some information in the stack. Okay. And this the machine code equivalent of this starts getting executed. Okay, int main. The first thing is that the parameters end up getting pushed onto the stack. Okay, this is how the compiler would actually sort of create this code. It's the compiler that has laid out the code that when it is compiled int main blah blah blah, at the entry point of main, the first thing that it does is push argc onto the stack. It's the compiler that has generated this code. Okay, so at runtime when this code is getting executed, argc, which is 4 bytes because it is int, got pushed onto the stack. Okay. Next, argv, which is a pointer. You guys don't understand pointer probably, but it's an 8-bit. It's an address. It's a memory address. Okay. So that got pushed onto the stack. Okay. Now our instruction pointer as program counter has moved to the print prime factors. So we are about to call print prime factors now. Okay. Abhi tak we have argc and argv onto the stack. Because we are about to call a new function, and that new function may be using the registers etc. in its own way. Registers, you guys remember register file, right? Any piece of code uses registers as scratchpad. Main function does not know what all kinds of register manipulation print prime factors might actually do. Okay, so what main does is, let me save whatever registers I have used up till now, let me save that onto this stack. Okay, from here on print prime factors is free to use all the registers, whatever it is, because whenever the function returns, main function can always restore its state using this. Make sense? Okay. So the main function ended up pushing some of its registers onto the stack, and then did a jump to this address. Remember, CPU can deal with only addresses, no names. Okay. How does the CPU know what address to jump? It was there coded right into the machine code instructions by the compiler, because the compiler knew what are the functions, so it determined some n number of addresses for those functions and put it onto the executable file. Okay, so we did a jump to print prime factors. Now print prime factors, just like main, the first thing that it does is pushes its parameters onto the stack. Okay, then push factors onto the stack. Okay. Now print prime factors is about to call the next function, prime factor. So the same thing happens. Let me save my registers first. Okay, so this pushing of registers onto the stack is so that print prime factors can restore its state when the code returns from the prime factors call. Are you guys able to follow this? This is super crucial. This is like the basic control flow of how calling functions works, irrespective of the language. Okay, so if there's any confusion about it, I would rather spend time here and not take up some of the other parts of this lecture and instead focus the time here. So it's very, very crucial that if there is any confusion, you guys call it out. Okay? If you don't understand this, rest everything will become very complicated for you. Okay? So print prime factors has now been able to, has pushed its registers onto the stack and then jumps to prime factors. Prime factors does the same thing, sort of stores its parameter onto the stack, calls, then pushes factor onto the stack, or rather makes space for it, factor IDX, okay, saves registers. Why does it save register here? New doesn't seem like a function. What is happening here? It saved registers while calling new. New doesn't seem like a function. It's like a C++ keyword.
Maybe internally it is doing something, like calling something.
Precisely. So in C++, new operator actually translates into a function call, which is implemented by lib std C++. Okay, it's not too different from when you in the JVM you get the new instruction. You will remember from the JVM class, right? That new was an instruction in the JVM bytecode, right? So when you call new, internally the JVM is still actually going to call a function to allocate the memory and stuff like that. Okay? So here also, that's because it essentially translates into a function. The compiler does that behind the scenes. Okay, so those of you who program std C++ sometimes, here's an interesting thing. New actually translates into a function. Okay, so that's why it actually saves its registers and then jumps to it and processes everything, etc. Does executes all of this logic, ultimately gets into the return step. The moment it returns, what should happen? Notice what has happened. For each function call, there is a part of the stack that they own. Correct? The main owns this. Print prime factors owns this much, and prime factors owns this much. Correct? Each one of this is called a frame, stack frame. Okay? So part of the stack, each of these functions owns. Okay? So the moment prime factors returns, all of that, the moment prime factors returns, what happens is that the position of the stack, the current stack pointer, is moved back to this. In physical memory, the previous data points might remain, okay, but they can now be overwritten by something else, or whatever pushes some new value to the stack. Okay. So the stack has, part of the stack has been unwinded. The whole frame was gone. The moment the whole frame is gone, what does it mean? All the variables that were there onto that particular frame are no more accessible. I mean, you can read technically from memory, but it's not guaranteed that the value is actually technically the correct value. Okay? Did you notice how the life of these variables in prime factors is intricately tied to the liveness of the stack frame? Do you see? What was the location of these local variables? Factor IDX, I, etc., etc. What was the memory location of that in the stack? You remember from that picture that I showed you? All local variables were showing up on the stack except for the ones that allocated by heap, right? Rest all of the local variables were showing up on the stack minus something. Remember that, right? The moment the stack gets unwinded, those local variables are gone. Poof, right? That's a big reason why local variables and the life of local variables is intricately bound to the stack frame. Any variable that you want to live beyond the call of the function, it cannot be on the stack. It will have to be on the heap. Did you understand? let's say you have a 12 byte structure, some some object, okay? If you store it on the stack, let's say prime factors stored it on the stack. The moment prime factors returned, this memory is not guaranteed anymore. Okay? So if some other function now points to, let me make it disappear. This is where prime factors Manyate had sort of allocated 12 bytes of some object. Okay? If some other function after the stack is unwinded, if some other function now tries to access it, the value of that object is no more guaranteed. Okay, it could have been overwritten, some corruption, or it might be zeroed out, depending upon what the compiler wanted to do. Okay, this is the reason why any variable, where the life of that variable is independent of the life of the call, cannot be allocated on the stack. That's also the reason why local variables are allocated on the stack, because the life of those variables is linked with that call stack being valid. Okay? So anyhow, prime factors has returned. We execute this. Now print prime factors is about to return after this execution. Okay? What will happen? Yeah, so the stack frame of print prime factors will now get unwinded, gone. Understood? So each function call pushes a new stack frame. And what is the size of the stack frame? The sum total of the size of all of its local variables. Okay? So main started with a stack called prime factors. So print prime factors. Print prime factors ended up pushing its own stack frame onto the stack, which called prime factors. So that pushed its own stack frame on top of the stack. Top is niche, stack goes outwards. Okay? Alright, so all of this is well understood. Life cycle of the local variable is tied to the stack frame. Can you guys see why? Okay. Any questions around this? If you do not understand this, rest everything will become super tricky to understand. This is how functions are called irrespective of the language. Whether you're using C++, Java in the JVM also, you remember there was each thread had actually a call stack, a stack frame to it. You guys remember that? Okay, exactly the same logic got executed. So this pattern plays out repeatedly. Okay. An assignment for you is, one of the things that we didn't discuss is how our return value is getting captured. So here we are returning a pointer. In main we are returning an int. Okay. In most of these standard architectures that you deal with, Intel or Apple's architecture, basic types are returned via registers. Okay. Complex types, if you are returning a struct, for example, or some kind of an object, okay, either an address of that object if the object is in heap, because if the object was on stack, you cannot return the value of that because it doesn't hold any value. But if you so complex objects, one of the ways of returning it in a non-heap way is by pushing it onto the stack immediately after the previous call frame's stack. Okay, so that's an assignment for you guys to figure out. I'm not going to go into this right now. So now what happens if, so whenever a new function call is happening, a new stack frame gets pushed. If there's an infinite call recursion, what happens? Yes, but why?
Because they have run out of memory.
Yes, so stack frame keeps on getting pushed, right? Like somebody was calling it out there. Stack frame keeps on getting pushed. Eventually you'll run out of memory. What was the amount of stack that was made available to us when I was showing you the layout? 7 MB. So the moment you have crossed 7 MB, at least on my machine, that process would die. Okay? There are ways you can sort of change the size of the stack, look into a command called ulimit on Mac OS and Linux machines. On Windows, you guys figure it out what is the right way to do it. But yeah, that's one way you can actually change the stack limit for a particular program that is done. The stack size. Okay, but stack size is fixed. Okay, and the way this is actually, the way these things are actually captured is why after data is this, that corresponding to a stack, usually there is a part of the memory that is sort of captured called stack guard. Okay, the moment anybody touches that particular memory, the operating system gets to know that an invalid memory access is actually being made. Remember that stack guard doesn't take up actual physical memory. Resident size is 0. Okay? And you know there is some virtual space of 56 MB of virtual space is carved out, but in reality there is no physical memory that has been allocated. So it's a guard. The moment stack overflows, you know, things end up, stack is growing downward, remember? So top of the stack, bottom of the direction I'm getting confused about right now, but the point is that the moment you end up sort of going outside of the stack, that's how somebody was asking me a question about how do we get to know that there's a stack overflow. That's how we actually get to know about the stack overflow, because it goes beyond its bounds. Okay?
Is there any reason for 7 megabytes?
Any reason? Stack area, remember, is linked with the maximum amount of function called depth you can encounter, correct? In practice, the amount of function called depth you will encounter is actually very limited. If you are going anything beyond 12 or 15, you know, function called depth, there's something seriously wrong that you know you are actually doing. Okay, so 7 MB is actually fairly liberal amount of memory space that has been allocated, which is another reason why a lot of languages, if you are declaring a local variable of a very large size, the compiler is going to call out that this much size is not allowed, something like that. In a lot of the languages, there are limits to how much you can actually allocate to the stack, because any local variable is going to go onto the stack. So if I say that int array 1024, 1 KB of memory is getting pushed onto the stack. Okay, so if I say 1 MB of array, 1 MB is actually getting pushed onto the stack. So because the stack is limited, compilers would also prevent you from allocating very large values onto the stack. Okay, so call function piece has been understood. We also understood why infinite recursion leads to stack overflow. One of the advantages of having a lot of these, one question that I put in the pre-read was, what is faster, stack or heap? Why is that?
Because stack has first of all fixed memory, and it has an order to access the variables. While heap, the local variables are stored in different places. There is no particular order of accessing them, and it is a
dynamic memory. So part of it is spot on. I think the part that is correct is the part that the reasoning seems to hold out is that the order in which you access the memory, every time you access the memory, there is a chance that it is going to get cached in the CPU cache, right? Okay, the more you frequently access something, the more something gets cached. And remember that if you are accessing a 4-byte value, it's not 4 bytes that get cached. It's the size of the cache line. If you remember from our very first lecture, 64 bytes is often the cache line size in your CPUs. In Apple, it is 128 bytes if I remember correctly. Okay, so even if you've accessed 4 bytes, 64 bytes are getting cached in the memory. So which means that if you accessed argc, argv also becomes cached in the memory. Okay, so which is why, because local variables are so sort of closely packed together onto the stack, the chances even, and local variables are the ones that you're using the most, usually inside a function, correct? Right? So you access one and the others become super fast to access. That's one reason why programmers like to think about that local variables are faster than something that is on the heap. Okay? It's not that heap value cannot be cached. It does get cached. But firstly, heap values are often larger in size. Okay? That's one reason to allocate them on the heap. And secondly, the allocation can often be spread out. Okay? The one object that I want is here, another object has been allocated somewhere, very different place. So even if I've accessed here, this guy does not get cached. Make sense? Okay? So which is the reason why stack is often considered as faster than heap. But like your friend here said, it's the access pattern that actually makes stack faster. There's nothing inherently wrong about the address of the heap. Technically both stack address and heap address are random places of the memory, and both will have equal latency. It's the fact that because stack is getting access usually far more, so CPU caches kick in. So the question is, if something like a Python, a dynamic language, what is the difference between a dynamically typed language and a statically typed language? Types are dynamic. Types are not known at compile time for dynamic languages, right? Which means that dynamic languages, along with the value, always need to carry some metadata, which captures the type of that. So even if in Python, if you have I is equal to 10, okay, it's not just a 4-byte value that is going to get stored. It's, I was checking on my machine, it was 28 bytes of metadata plus 4 bytes of value. So 32 bytes for accessing a variable, that's actually just 4 bytes. 32 bytes got allocated onto the stack. Okay? So in just 2 variables, my cache line is actually full, absolutely filled up. You understand what is happening here? Okay? That's a big reason why dynamically typed languages are slow. Along with obviously there are more runtime checks around the typing, etc. But even from a perspective of efficiency of memory access, they become slow because they have very fat variables. Fat variables are not good for caching. That's a big reason why dynamic languages end up being slow. Understood? Okay. Let's go to default parameter values. Some languages allow you to have, like in C++, you can have some of these parameters with default values, which means that I can call this function sum with just 1 parameter or 2 parameters or 3 parameters. Okay? And just to demonstrate it, I have a bunch of these example invocations called up. Okay? This I'm showing. This is LLVM is a big compiler framework that is often used for a variety of different languages. So this is like an intermediate representation. You guys remember intermediate representation from our previous lecture? So this is like a precursor to getting into assembly. You don't have to understand all of this. Okay, we'll focus on the conceptual pieces of it. So notice what this sum function translates into. Even though I've defined default parameters here, there is no notion of default parameters that are showing up in the intermediate representation. All that is showing up is all the 3 parameters. And notice alloc A is actually allocate space on the stack. This is what I meant by pushing something on the stack. Remember, when a function is getting called, its parameter is getting. So 3 parameters, space got allocated, and then stores value of these registers that we receive the value from end up getting stored on these stack. Okay, so that is all that this means. But the main point here is that there is no default parameter that you see in the definition of this function. Okay. But when I am calling this sum1 function, notice what it does. It calls this function here with value 1, which corresponds to the value 1 here, and the other 2 values are 0 and 0. How is the compiler able to do it? Because at the compile time, it can see both the functions. At compile time, it can see when it was compiling sum 1, it was able to see that sum B and C parameters have a default value of 0. So compiler has access to this information at compile time, so which is why it's able to do it. Okay? Is this making sense to you? Any confusion about this? Default parameter implement. This is how compilers end up doing it. Okay? Kotlin is a language built for the JVM. Anybody who's programmed here in Kotlin? Okay, a few hands. Okay? So for those of you programmed in Kotlin, I'll encourage you to figure out by looking at the bytecode implementation. I'll encourage you to figure out how default parameters get implemented in Kotlin. It's slightly different than this. Okay? Okay, let's look at the another thing, function overloading. Anybody, do most of you here understand the word overloading?
Yes.
Right? What is overloading?
The same function for different
Yeah, so same name but different signature.
Yes.
Right? So I have two functions here, same name, sum, but the signatures are different. One is an integer sum, another is a long sum. Long is like 64 bit wide number, int is 32 bit. Okay? So for the first sum, implementation is like, you can see I32 being used. Second one is I64 being used. So it generated two different implementations, one for each kind of signature. Okay. At the compile time, when I'm compiling test int sum, based on the type of the value that I use, does the compiler know which sum function to call?
Yes.
Yes. Okay. Which is what happens. So that is how function overloading is resolvable at compile time. Okay, by looking at this. So compiler does it for you. The CPU doesn't have to do any hard work. Understood? Okay. By the way, just these random names like Z3, some II and stuff like that. This also tells you that when it comes to machine code, it's absolutely nothing about name of the function that is making. It's only addresses. This intermediate representation, by the time it actually gets compiled into assembly, is like will have nothing remnant of the name of it. Understood? Okay? Yeah. All right. We'll not be able to cover everything, but I think let's see what we can. Classes. This is a class similar to your, not very different from your Java classes. Some variables, some member variables, some functions. One constructor and one function. Okay? All right. How does this get implemented? I think first thing is, again, I'm using the I'm using the intermediate representation of the compiler to demonstrate to you. Okay. Focus on the conceptual pieces and not exactly on the exact syntax or something like that. First thing is, how many member variables were there? 3 of type I32, 32-bit integer. So which is why every time I create a new employee object, how much space is going to get put onto the memory? Quickly. 96 bytes. Bits, yes, right? So 12 bytes, right? 4 bytes for this, 4 bytes for this, 4 bytes for this. Okay? Salary per year function. Remember, it's a member function. So how do we invoke a member function? We create an object, and that object dot the member function. Standard syntax in most languages, correct? Okay. But let's look at, remember, CPU does not know any encapsulation. It all it knows is addresses and stuff. So how does this map on to the actual machine code implementation? Salary per year of experience is going to get implemented something like this. Return type is int, so I32. Okay. What is it? Does salary per year of experience take in any parameter? Here, in the source code, do you see any parameter? No. In the generated code by the compiler, the intermediate representation, do you see any parameter? Yes. What is that? The no, return type is int. So return to I32. But here there is no parameter, and here you see a parameter of type pointer.
It is pointing the object.
Yes.
We
Right?
have defined earlier, employee.
Right? So when we create an employee E something, okay, then when we created employee E, those 12 bytes got put somewhere onto the either on stack or in heap, depending upon how we coded it away. So this one is coded away as stack, so this will get allocated onto the stack. Okay? So these values got created. Okay? When we called e.salary per year of experience, what happens is this function gets invoked, okay, with the object's address as its parameter. So when we say e.salary per year of experience, it is equivalent to some function salary per year of experience with the parameter as e or address of e. Make sense? Because in the machine code there is no notion of encapsulation. It's only addresses everywhere. This notion of encapsulation is in the language, not in the machine code, not in CPU. Okay, so whenever you call a member function, it's equivalent to calling a global function with that object as the parameter. This, which is the keyword used in a lot of languages to represent the current object instance, is just a parameter to a flat function. Okay? Understood?
Yes.
Alright. To demonstrate it, you can use .memlens demo class. Notice, so this is the logic. We create an employee, okay, and we call employee.salary per year of experience. Where is the address of employee? Yeah, main local var employee, stack -3132. Inside the function, inside the salary per year of experience function, I'm also showing the address of this. What is the address?
Same address.
Same address.
Same as
Exact, right? So do you see this? Do you see what I'm trying to show you?
this password.
The first, this one, stack, the first stack -3132 that you are seeing here, this one. This address I'm showing you from the main function. Okay? Which is the address of this employee. Okay? Whereas this one, this stack -3132, I'm showing from inside this salary per year of experience by referring to the variable this. I'm not using the variable EMP. I'm not showing you, I wasn't trying to show you the address of EMP, but when I access this, the address of this was the same as that of EMP, which demonstrates what I was trying to prove to you earlier, that this is just a parameter to the function, and the parameter contains the address of the object where it is allocated, those 12 bytes that were allocated. This is just a parameter to a flat function. So whenever you come across something like class member function parents, this essentially translates into some random name of the function, this pointer to that object, and then the rest of the parents. Okay? This is a simple concept. And whenever you have a static function, like static void main that you see in Java, okay? Yeah, so that would essentially, so that doesn't rely on any object instance to be created, correct? So it doesn't take in this pointer. Understood? there is no encapsulation in machine code. Okay? So when we are programming in an object-oriented language versus when we are executing completely different things. Trying to think, we are. Okay, I'm going to skip this one because it will take up at least 10 minutes and I don't think we have that much time. You guys can go through the slides and see if you understand what I need to say. Let's see if very quickly. Huh? Const area is if you have any strings or anything that needs to be retained, a global static const variables, anything that cannot change and needs to be retained in the executable file goes into the const area. Try catch. Let me quickly walk you through. Stack frames, you guys remember from just like 10 minutes back, right? So let's say main calls a test throwing function, try catch block. Main calls test throwing function, which calls another function, which throws an exception. So this guy throws an exception, okay? The way try catch is implemented is, by the compiler is there a try catch block inside the throwing function? If the answer is no, unwind the stack. Unwinding, you guys remember, right? Just move the stack pointer up. Okay? So then the code would again check, is there is there a matching handler? So try catch might exist but no matching handler. So again, unwind. Then it will go to the main. Does this have a matching handler? Yes, then execute the handler. This is how try catch effectively works. Something that you guys knew, but with the knowledge of stack frames, now it's hopefully become a little more complex. Now, the exact mechanics of how it's implemented, I don't have time for, so I'm going to skip this. Yeah, dynamic linking is the last part, so let me this is something that I feel most engineers should know, but most don't. So let me just quickly talk you through. This should take up a lot of time. So in machine code, let's say you are calling a function called printf. So in your source code, you had written some printf or something like that, some print function, which actually lies in some other library. Okay? What happens when the executable is compiled? That is what this one is about. How is address of printf resolved? Because whenever you are calling a function, remember, the compiler essentially converts it into an address and jumps to that address. Right? That is what calling a function means. In this case, the address is not known because the printf lies in some other library which is going to get linked to us at runtime, not at compile time. So we don't yet know what the address of printf is. To understand this, let's separate out compile time and runtime. The way it is done is something like a global offset table, where what I do is I create this symbol printf. It actually goes in as a symbol printf, and address of printf is 00. Okay. This same thing goes up in the runtime also. And in my machine code here, what the compiler would do is, I know that the programmer called printf, so let me instead create a stub called printf at PLT. Okay, PLT is a short form for procedure linkage table and something like that. Okay. So this function the compiler has inserted, and the address of that function, let's say, is 123456. The logic of this function is implemented as load the address of printf from GOT and then call that address. Okay? So it's like a trampoline. I go here, get the address of the function, jump to that address. Instead of calling that address directly, load the address, jump. Okay? So now at wherever place the programmer called printf, I'll just call that address, this address, my stub function. Okay? The same thing shows up on the runtime also, and I will call out that which library printf is supposed to be in, and I include that as part of the compile time image. at runtime, the loader, when we load a program, when we execute a program, there's something called a loader that runs. It resolves libc.so in some exact location and loads that into the memory. In the virtual memory space, it loads the executable part of this libc onto the same address space of the process. And there it finds that printf is located at this address. And why was it looking for printf? Because global offset table had entry for printf. So what it will do is, this address, it is going to overwrite in global offset table. So now whenever I called printf in my code, it jumped to printf at PLT, loaded the address from GOT, which was the correct address, and called that address. So this method is called trampolining, but remember that it is one hop away. I first load the address from GOT and then call that address. Every memory access has a latency. Remember your first lecture? Okay, so which is why dynamically linked libraries are always a tiny bit slower than statically linked libraries. Okay, and this becomes important in certain high performance scenarios. Okay, so these are the files you can compile for yourself and play around with it. This is what we ended up covering. Large parts we ended up missing, largely because didn't have enough time. But that's it. Thank you. This was the last lecture in this series.